time step, and grid size, assuming that delta x is fixed. So we derived till here this e raised to the power delta t came out to be equal to 1 minus 4 alpha delta t by delta x square sine square km delta x by 2, where km is the wave number for the mth mode of the Fourier series. So mth component of the Fourier series, and we are doing it only for one m. So we derived this expression. Now we said that mod of e raised to power delta t should be less than or equal to 1. So let us now take the mod of this. It will be mod of 1 minus 4 alpha delta t by delta x square sine square, let us call it some theta. Okay, so now this should be less than or equal to 1. Now all of you might have some experience with solving inequalities like this. So what we'll do is we will remove the mod symbol here and write two separate equations, or we can write them in one equation like this. So whatever is inside this mod should be between -1 and 1. Only then this mod will be less than or equal to 1. So we'll say this should be greater than or equal to -1, whatever is inside the mod delta x square sine square theta, and it should be less than or equal to 1. Now again we will take this one that is here to both sides. To the left hand side of this equation, this is one equation, and to the right hand side of the other equation. These are two separate equations, but we are writing them as a single equation. There are two inequalities here. So this becomes -2 minus 4 alpha delta t by delta x square sine square theta less than or equal to 0. Now if you see this equation, the second equation, second inequality here, delta t is positive because it is a time step. Delta x is also positive. It is a grid size. Alpha is thermal diffusivity, which is also positive. Sine square theta is also always positive. Therefore, negative of all of this has to be negative, right? Therefore, this is always less than or equal to 0. Therefore, this is always true. This part is always true. So it is valid for any delta t, delta x, alpha. We don't need to solve that inequality. Now let us focus on this part, the first inequality here. Let us multiply by negative sign or just take them on the opposite sides. Take the right hand side to the left hand side to the right hand side. You can, yeah. So this becomes 4 alpha delta t by delta x square sine square theta is less than or equal to 2. This becomes alpha delta t by delta x square sine square theta less than or equal to half. Now, if you note what is our theta, theta was km delta x by 2, this one, and km depends on the different Fourier modes m1, m2, m3. So we don't know actually what those modes are. So we will consider that they range from minus infinity to infinity. Okay, so we want to derive this equation so that it is valid for all kinds of Fourier modes. So we are being very conservative here. We are assuming that there are all sorts of Fourier modes here. So we'll say that sine square theta can assume any value between 0 and 1 because it has to be positive. It can be 0 or greater than 0 and less than or equal to 1. Therefore, we will consider the highest value this can achieve, because if we consider any value less than 1, it will be a less conservative estimate of the bounds on alpha delta t by delta x square. So we'll assume that let us say that this is 1. Then alpha delta t by delta x square comes out to be less than or equal to half. And if we take alpha delta t by delta x square always less than or equal to half, then whatever mode we take, whatever value of sine square theta we take between 0 and 1, this condition is always satisfied. Okay, so this is our estimate that it has to be less than or equal to half. And this is what we saw in the MATLAB code, that when we took this value exactly equal to half, the error was slowly growing. Okay, let me show that again. If I run this, you saw this kind of graph here. After some time steps, I think this was 100 or so. Yes, so here you see that it is nt equal to 100. Okay, and n is going from 1 to 200. So after 200 time steps, you see some errors that appear there. The error is not growing very fast, it is not blowing up, but still there are some errors that we have seen. So it has to be less than half, then the solution would be stable, otherwise it is unstable. Okay, then anyway you are solving that assignment for implicit method, there you have to give me the condition on alpha delta t delta x square for which it will be stable. Okay, so now let us go to another kind of equation. Let us talk about a wave equation. Okay, a wave equation uh, can be written as a first order wave equation or a second order wave equation. We'll talk about first order because it is easier, but generally if you want your wave to travel in all the directions, then it has to be a second order wave equation. So let us consider a first order wave equation. Where c is the wave speed or wave velocity, u can be the displacement, uh, t is time, x is the distance. If this is a wave on a string, then from some mean value, this is u as a function of x and t, this is x, okay, from some origin. Now let us consider FTCS discretization, and also one more thing here, this wave velocity, it can be either positive or negative. Okay, in this case we are considering c positive. It doesn't matter for FTCS, but it matters here in which direction the wave is traveling. That will tell us if the solution is stable or not. We'll see that later on, but let us first derive the difference equation here. So we are talking about FTCS right now. forward in time and central in space. Okay, and we are at ith grid point plus C, and let us say, so because this is forward in time, the indices in time will be n here when we are discretizing with respect to x, minus I minus 1 by 2 delta x, okay, equal to 0. Now this equation will also be satisfied by the error between the exact difference solution and the numerical solution, which is the round off error. So we can write epsilon n plus 1 minus epsilon by delta t plus c epsilon I plus 1 minus epsilon I minus 1 by 2 delta x. The round off error satisfies this equation. Then we will replace one mode of epsilon here in this equation. We said that it can be written as e raised to the power at times e raised to the power iota kx. Actually, I should write different symbols for the space index and iota. Let me write that as j for now instead of iota. So e raised to the power at, this becomes at plus delta t because it is at n plus 1th time step, which corresponds to time t plus delta t. And e raised to the power j k, which is km you can call, or simply k, and x minus e raised to the power at e raised to the power j kx. So instead of iota, which is the imaginary number square root of minus 1, we are writing j. So remember that j is square root of minus 1 here. Divided by delta t plus c e raised to the power at jkx plus delta x, because this is I plus 1th grid point, minus e raised to the power at e raised to the power jkx minus delta x by 2 delta x equal to 0. Now we can take out some terms from here and cancel them from this equation. E raised to the power at and e raised to the power jkx, these are common. So we get e raised to the power a delta t minus 1 by delta t plus c e raised to the power jk delta x minus e raised to the power minus jk delta x by 2 delta x equal to 0. Now what is finally needed is mod of e raised to the power a delta t. So let me know what this is. Mod of what? On the right hand side. And if you can reduce it in terms of sine cos, then do that. And let me know what this is, so that we can then find out the condition on C, delta t and delta x for stability. This should be very quick. So this G is also known as amplification factor. Okay, some of you have given the answer. 1 minus C dt by dx and cos term. Uh, so why should there be a cos term? Let us write it again. So there is a negative sign in between. So you will have cos jk delta x plus j, we are writing, sorry, cos k delta x plus j sin k delta x, and then from the second term we will have minus so right now I'm just writing this part here, it is not equal to this. Okay, and minus cos k delta x, and there is minus minus plus j sin k delta x. So these both cos terms will cancel out. Okay, so some more answers. 1 minus c dt by dx into sine. Okay, let me just write this. E raised to the power a delta t mod of this will be equal to 1 minus c delta t by delta x, and there is a j here, sine k delta x. Okay. Oh, when you take it to the right hand side, it becomes plus. So this is a plus here. Okay, so that answer was correct. So now when you take a mod of this complex number, it becomes 1 plus c delta t by delta x whole square, and also sine k delta x whole square. Now we want this to be less than or equal to 1. Okay. Now can you tell me the condition for c delta t by delta x when this is possible? It can be seen that this is not possible from here, because there is already 1 added here, and this is always positive. So it can never be less than or equal to 1. It is only possible if the second term goes to 0. But for any general mode, when sine theta is not equal to 0, this is only possible when delta t goes to 0 or delta x is infinitely large or speed is 0. So practically that condition will never arise. So this is unconditionally unstable. That's what we say from here. Sorry. This is a wave equation. This is a hyperbolic kind of equation. That's what we have studied. If you write it as FTCS difference equation, you cannot solve this on a computer. Okay. But a heat equation you could still solve, but there was some condition which has to be met, that alpha delta t by delta x square has to be less than or equal to half. That was the condition. Now what you have to do is, because this came out to be unstable, now you go to some other scheme, okay, apart from FTCS, and see if that is stable or not. So this is what we as CFD people have to do. We have to test out different schemes. There can be some physical reasons, you can have some mathematical or physical reasons, some reasoning you can use. So what people found for wave equations, for hyperbolic equations, is that if you use an upwind scheme, what that means is, let's say you have this uh, as your one dimension, and there are different points here where you will get your wave height, okay, and the distance between them is delta x. This is an equidistant grid. If the wave velocity is in this direction, then while differencing the space derivatives, so this is the spatial derivative dou u by dou x, while writing an approximation for that, you have to consider an upwind derivative, which means that if you are at point I, let's say this is I minus 1, this is I plus 1. If you are at point I and you want to calculate the derivative, you write the difference with this point and this point. Don't use I plus 1th point, which is in the direction of wave velocity. Use the upwind. So this is known as the upwind point. So the analogy is that if the wind is blowing, then the upwind or upstream point you have to take. If the wave velocity is negative, that is in this direction, and you want to calculate the derivative at point I, then you should consider I plus 1th point. Okay. So if it is given that C is greater than 0, okay, and now we are not taking the central difference because we want to consider only the upwind point. That's why we cannot consider I plus 1th point. Therefore, no central difference in this case for the simplest derivative. But as we discussed earlier, we can have one-sided derivatives. So you can still consider I minus 2, I minus 1, and I, and calculate a second order accurate expression. But for now, let us just take a first order accurate expression. In this case, backward difference. So for the time term, it will be still n plus 1 minus un at I by delta t plus c times dou u by dou x, which is ui at n minus ui minus 1 at n by delta x equal to 0. If you calculate the uh, stability condition for this equation, you will find that you will get some region where it is stable for some conditions. And because this C will appear there, if you set C as negative, you will again find that it is unstable. If C is positive, only then you will find some stable condition for stability. Similarly, if it is given that C is negative, you can write this as C times ui plus 1 minus ui by delta x. Okay, the discretization of the space derivative. So this is for C less than 0, and this is for C greater than 0. If there is any question, you can ask now. Okay. So now, okay, I will not derive this here. What it gives is that C delta t by delta x is less than or equal to 1 for positive C. And if C is negative, a similar expression will come. C delta t by delta x, you can say mod of this, is less than or equal to 1 for C positive or negative. This is also known as CFL condition or CFL criterion for stability. This CFL, these are the names of scientists who worked on it: Courant, Friedrich, and Levy. Okay, and what it physically means is that if these are the grid points, and the wave is traveling in this direction, then what is C delta t? C delta t is the distance traveled by the wave in time delta t, right? Velocity times time step, that gives you the distance. So in one time step, you cannot go more than the delta x distance. So if your wave height, let's say the wave looks like this, then in one time step you are allowed to go only till here. you cannot go, you cannot skip a grid point and go till somewhere here, then it will become unstable. That's what this CFL condition means. Okay. Is there any question? I hope this is all clear. Okay. Now for this case, I can also tell you what G is. In case of the thermal diffusion equation, G was not a complex number, but in this case, as you have seen, for the central difference case, it came out as a complex number. Then you had to take a mod of that complex number to get a real value of mod G. For the upwind scheme, G is 1 minus C delta T by delta X plus C delta T by delta X cos theta. Let me write it as theta, which is K delta X in this case, minus J C delta T by delta X sine theta. Okay, where theta is K delta X. You can write this G as, because this is a complex number, mod G e raised to the power J phi. J is still square root minus 1, where phi will be equal to the angle this complex number makes on the Argand plane, that is minus, let me also call C delta T by delta X as nu. So minus nu sine theta by 1 minus nu plus nu cos theta. Okay, this is the angle, and mod G is the mod or magnitude. And here mod G in this case is 1 minus nu plus nu cos theta whole square plus minus nu sine theta whole square, which is also nu sine theta square, and the square root of that. Okay. Now there are more things we can do with this G, which is not related to stability as such. So you notice that what we said here is that the error satisfies this equation, as well as the difference equation solution, that is U, also satisfies the same equation. So if the solution is periodic, that is, if you can express that also as U equal to e raised to power at e raised to the power I kx, iota kx, then you will get growth or the amplification for U also. Till now we have derived amplification or growth of epsilon, because we said epsilon is e raised to the power at e raised to the power I kx. Okay, expressed it as Fourier series. But now you can also get the growth factor or amplification factor for U itself. Okay. So this g that we have obtained is also valid for u itself, for the difference equation solution itself. And if you want to know the amplification or growth in time for the actual solution of the exact partial differential equation, that is dou u by dou t plus c dou u by dou x equal to 0, what you do is, assuming that u is equal to e raised to the power some alpha t e raised to the power I kx, substitute it here. Let us do that. When you take derivative of e raised to the power alpha t e raised to the power I kx with respect to time, you will get alpha e raised to the power alpha t e raised to the power I kx, and the second term that you will get is c iota k e raised to the power alpha t iota kx equal to 0. So these two terms you can cancel out. From here you get alpha is minus iota kc. Now you got the solution e raised to the power alpha t, which can be written as minus iota kc t iota kx. Now to find how this solution changes with time. In time, what happens to this? We just have to do u at t plus delta t divided by u at t, or un plus 1 by un. But because this is a continuous domain solution, the time step is not discretized. The time is itself is not discretized here. We are writing u at t plus delta t and u at t. Okay. So this will be equal to, if we take the mod of this will be equal to e raised to the power minus iota kc t plus delta t iota kx divided by e raised to the power minus iota kc t iota kx mod. Iota kx cancels out, t and this one cancel out. You get e raised to the power minus iota kc delta t. And what is the mod of this? E raised to the power iota theta mod is always 1. So we see that for the wave equation, mod of the amplitude difference or the amplification in magnitude is equal to 1 always. It doesn't decay or increase. The magnitude remains the same. But now we want to compare this with the numerical solution. What happens to the numerical solution? Exact solution, we obtained this fact, we know about this, that it has to stay the same. If there is a wave like this traveling, the magnitude will remain the same. It will just change position. Magnitude will remain the same. That is the exact solution. But what happens numerically? So let us see that. This is the numerical amplification factor that we have obtained. Mod G. And it of course depends on theta. But if you take that as 1, you will get 1 minus nu plus nu square plus nu square for one particular mode. And you can plot it versus with respect to theta on a plane. Okay, so G versus theta, you can plot something like this. and you will get something, some curve. But you can observe that this is not equal to 1. The numerical solution that we get is something else. Is it greater than 1 or less than 1? Uh, can you find out from here? Is it greater than 1, less than 1, or sometimes greater than 1, sometimes less than 1? Please let me know in the chat window. So take some value of nu. We have derived that C delta T by delta X, which is equal to nu, has to be less than or equal to 1. That is the stability condition. So take some value between 0 and 1 and find out. You can actually find a derivative with respect to nu and see for which value it is maximum or minimum, and you can do that analysis. But you will find out that it is always less than 1. Okay, it has to be less than 1 because nu is less than 1. All right. So numerically what happens is, this is known as numerical dissipation. So the exact solution is not dissipating, or the energy is not dissipating, you can say. The height or the magnitude of the wave is not decreasing. But when you just discretize the equation, you introduce some numerical dissipation just by discretizing it and solving it on a computer. So if the initial wave height is like this, after some time, it is going to decrease as it moves. Okay. So this is a concept called numerical dissipation. This is very important to note. Just by discretizing it and solving it on a computer, you change the characteristics of the equation. The original equation did not have any dissipation, but now you have some dissipation. So similarly, let's say you are solving Navier-Stokes equations and you want to solve for inviscid flow where there is no viscosity, and you set viscosity equal to 0. Let me write the Navier-Stokes equation here. Dou u by dou t plus u dot del u density multiplied by this minus del p plus mu del square u. This is the equation without any gravity and other terms, other force terms. This is viscosity. Even if you set viscosity equal to 0, you are going to see in your code that there is some viscosity anywhere. Just because it is discretized and you are solving it on a computer, there is some viscosity that is automatically introduced. That is known as numerical viscosity. So no matter what you do, it is always there. This is numerical dissipation. Similarly, there is one more concept where the Fourier modes of the original wave are not preserved. So sometimes you will see that the original wave, if it looks like this, here it may not be, you may not get a proper feel of that. Let's say the original wave is like is like this, and what will happen is it will dissipate over time. That is, the magnitude will decrease, And also you will see that some Fourier modes will come out like that. So this is known as numerical dispersion. All the waves will not have same velocity. Some waves will lag and some will lead. Some Fourier components will start leading and some will start lagging. So the final solution you will get will look like this. This is known as numerical dispersion. So similar to this mod G that we analyzed here, mod G versus mod GE. So the exact solutions amplification factor and numerical solutions amplification factor. So this is what we use to analyze numerical dissipation. Similarly, you can analyze the phi, which we derived here. Phi was the angle, okay, the argument of this complex number, and the phi exact. So phi versus phi exact. You will see that the phase angle doesn't stay same as the original exact phase angle for all the Fourier components. Some Fourier components will start leading and some will start lagging. So this is known as numerical dispersion. This can also happen in numerical solutions. So what you want is you want to minimize both of these things, dispersion as well as dissipation. Is there any question? Okay. And it depends, no need to say that it depends on the type of scheme that you use, the kind of discretization you use, first order, second order, central, forward, backward. All of these have different properties of dissipation and dispersion. So in the next class, we will also try to see, we will try to analyze it. We will not derive it for all of these schemes, but I will just show you what they look like for different schemes. So as CFD people, scientists try to come up with different schemes which minimize these two things, dispersion as well as dissipation, okay, to approach the exact solution on a computer. So that's all for today. If there is any question, you can ask now, or if there is any question on the assignment, tomorrow is the last date for submission, you can ask now. Okay, if no, thank you.